Hello my dear student, welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today we are going to talk on module titled Introduction of Two-Dimensional Material under the paper Nanoscience and Technology 2. After completing this module, the student will able to learn about the two-dimensional material or quantum well on the basis of quantum confinement. You will learn to calculate the density of state for quantum well structures. You will also learn to calculate the occupancy of conduction band, valence band. Also, you will able to learn to calculate the Fermi level of quantum well structure. Examples of several experimentally synthesized 2D materials. When the size or the dimension of a material is continuously reduced from a large or a microscopic size, such as a meter or a centimeter, to a very small size, the properties remain the same at first. Then small changes begin to occur until finally when the size drops below 100 nanometer. Dramatic changes in the properties can occur. If one dimension is reduced to the nano range while the other two dimensions remain large, then we obtained a structure known as two-dimensional material or a quantum well. If two dimensions are reduced in a nanometer range and one remains large, then resulting structure is referred as one-dimensional material like a quantum wire. If all the three dimensions are reduced in nanometer range, is called zero dimension, and materials are like a dot and known as quantum dot. The word quantum is associated with these three types of nanostructure because the changes in properties arises from the quantum mechanical nature of physics in the domain of ultra small. I want to discuss the quantum confinement 2D, 1D, 0D system. A major feature that discriminate various type of nanostructure is their dimensionality. The word nano stems from a Greek word nanos, which means dwarf. This word nano has been assigned to indicate the number 10 to the power minus 9, the 1 billionth of any unit. All the existing material can be characterized into four broad categories on the basis of quantum confinement, such as if the electrons are free to move throughout the material in all the three directions, such as x, y, and z, such materials are known as 3D or bulk materials. Density of state in this case looks like parabola along the energy axis. Now, if we restrict the motion of the electron from one direction, let's say along the x-axis, and allow electron freely to move in the other two directions such as y and z, such materials are known as two-dimensional materials. And density of state in this case looks like stairs, which is clearly shown in figure. Several two-dimensional material has been discovered, followed by the discovery of graphene. which I will discuss in detail in coming slides. If the motion of electron is confined from two directions such as x and z and allow it to freely move along the only direction such as y, then this kind of material are known as 1D or quantum wire. The density of state in this case looks like spikes with narrow broadening. One can see in the figure. And finally, if motion is confined from all the three directions x, y, z, this kind of material are known as 0D or quantum dot, and density of state is such kind of material looks like spikes, which is similar to the atomic spectra in case of atom. Now, in the coming slide, we discuss in detail the 2D materials or quantum well-like materials. I am going to talk particle in two-dimensional box case. Now, we will discuss the two-dimensional material in detail. This kind of material are similar to well-known problem of quantum mechanics, which is particle in two-dimensional box. Now, to truly have complete information about the system of interest, we should know all of its possible energies and wave functions. However, our past experience solving the Schrödinger equation shows that many valid energies and associated wave functions exist. Complicating this, in certain cases, degeneracies are possible, resulting in states that possesses the same energy. As a consequence, the task of calculating each and every possible carrier wave function as well as its corresponding energy is impractical to say the least. Let us now consider a particle in a two-dimensional box. Assume that a particle is confined to a square box with a dimension A within xy plane. The potential is 0 inside the box and infinite outside. Solving the Schrödinger equation lead to the following wave function shown in equation 1.1. Psi nx ny equal to 2 by a sine nx pi x by a sine ny pi y by a, with corresponding energy which is shown in equation 2 equal to n square h square by 8m effective a square, which equal to h cut square k square 2m effective, where n square is nx square plus ny square and nx is 1 2 3 and ny is 1 2 3 etc. And k square is equal to kx square plus ky square, where kx is nx pi by a and ky is ny pi by a. List of the first 10 energies of the particle is shown in the figure. Illustrate that the first 8 energy levels with their degeneracies. Now I want to discuss the density of state. Here I will be discussing the density of state of quantum well. The density of state of quantum well can also be evaluated, as with the bulk density of state evaluation. Density of state of a quantum well or 2D material is like following. Density of state of a system in solid state condensed matter physics describe the number of states per interval of energy at each energy level available to be occupied. Unlike isolated system like atom or molecule in the gas phase, the density distribution are not discrete like a spectral density but continuous. High density of state at a specific energy level means that there are many states available for occupation. Zero density of state means that no state can be occupied at the energy level. In general, we can say a density of state is an average over the space and time domain occupied by the system. Here, we will discuss the density of state for quantum well structure in detail. The density of state of a quantum well can be evaluated by considering a circular area shown in figure, with radius k is equal to under root kx square plus ky square. After following few mathematical calculation, one can get the expression for density of state, which is written as rho e equal to m effective by pi h cut square summation over nz theta e minus e ng, where Ez is the index associated with the confinement energy along the z-axis and E phi E minus E nz is Heaviside unit step function, defined by theta E minus E nz is 0 if E is less than E nz and is 1 if E is greater than E n. If we plot this function with energy, it looks like a stairs which has been shown in figure. The occupation of valence and conduction band in quantum well. Using density of a state expression, one can calculate the occupation of conduction and valence band. Detailed calculation has been shown in the content of the unit section. Occupation of conduction band Nc is proportional to or equal to me kt by pi h cut square e to the power minus ef by kt, and occupation of valence band Nv is mh upon pi h cut square integration minus infinity to enh e to the power minus ef minus e by kt de. First sub-band, which is shaded one, of the conduction band and valence band in the quantum well has been shown in the figure. For comparison purpose, the dashed line represents the bulk density of state for both the electron and holes. What could we do with layered structure with just the right layer? Asked Richard Feynman in his famous 1959 lecture, "There plenty of room at the bottom." With the help of the amazing development of the past several years, we are coming close to answer that question. Whereas thin layers and multi-layers of various kind have long been known to technology, researchers are now learning to create uniform, atomically thin layered and manipulate them into novel solid with a broad range of physical properties. Followed by the discovery of graphene, several two-dimensional material have been discovered and many more have to come. Till date, several families of two-dimensional material have been discovered, which spans whole the electronic material ranging from metallic to insulator in nature, such as graphene family, black phosphorus family, group 3,6 family, and TMDs family. Example of graphene for 2D material. As you know, graphene is an allotrope of carbon in the form of two dimension. Atomic scale, hexagonal lattice in which one atom forms each vertex. It is a basic structure element of other allotropes including graphite, charcoal, carbon nanotube, and fullerenes. It can be considered as an indefinitely large aromatic molecule, ultimate case of the family of the flat polycyclic aromatic hydrocarbons. Graphene is the first experimentally synthesized material which provides researchers to extremely verifying whole the theory set for the two-dimensional structure such as particle in a box. Graphene has many unusual properties. It is about 200 times stronger than strongest steel. It efficiently conducts heat and electricity and is nearly transparent. Graphene shows a large and nonlinear dimagnetism, greater than graphite, and can be levitated by the niobium magnet. Graphene has been discussed in detail in another module named as Introduction, Synthesis and Characterization of Graphene. Transition metal dichalcogenides, another example of 2D material. TMDs has been discussed in detail in the module named as Introduction, Synthesis and Characterization of TMDs. In brief, here I want to say that TMDs are layered material. One metal atom M is sandwiched between two chalcogen atoms. Weak van der Waals forces exist between two adjacent layers. Due to the presence of weak van der Waals forces, TMD can be exfoliated. From top 2H phase looks like hexagonal with alternate metal and chalcogen atom, and 1T phase looks like a two interpenetrating hexagons. General formula of TMDs are Mx2, where M is the transition metal and X is the chalcogen. Hexagonal boron nitride, known as HBN, a layered material similar to graphite, is a promising dielectric. Monolayer HBN is crude white graphene isolated from bulk BN could be useful as a complementary two-dimensional dielectric substrate. This hexagonal boron nitride is also called white graphene as written there. Using CVD technique, large area monolayer hexagon boron nitride could be grown. This atomic film shows a large optical energy band gap of 5.5 electron volt and are highly transparent over a broad wavelength range. I want to discuss another example of 2D material, which is phosphorine. Phosphorine is a monolayer of black phosphorus, is known as phosphorine. Phosphorine is semiconductor in nature, having band gap of the order of 0.5 electron volt. Phosphorine could be easily obtained from a mechanical exfoliation of a black phosphorus. And black phosphorus layer also have an anisotropic structure unique among layered material. Individual layers are buckled with two in-plane mutually perpendicular directions having armchair and zigzag edges. The structural anisotropy strongly influence the electronic property in these two directions. I want to discuss Amaxine, which is another 2D material. In material science, Amaxine are a class of two-dimensional inorganic compound. These materials consist of few atoms thick layers of transition metal carbides, nitrides, and carbon nitrides. First described in 2011, Amaxine combine metallic conductivity of transition metal carbides and hydrophilic nature because of their hydroxyl or oxygen terminated surfaces. As synthesized Amaxine prepared via HF etching have an accordion-like morphology, which can be referred to as a multi-layered Amaxine or ML Amaxine, or a few layer Amaxine, which is FL Amaxine, when there are fewer than 5 layers. because of the surfaces of Amaxine can be terminated by functional groups. The naming convention Mn+1 XNTX can be used where T is a functional group, for example, oxygen, fluorine, or hydroxyl group. Amaxine adopts three structures as inherited from the parent MAX phage. For example, M2C or M3C2 and M4C3. They are produced by a selective etching out the A element from MAX phage, which has the general formula Mn+1 AXN, where M is the early transition metal, A is an element from group 13 or 14 of the periodic table, and X is carbon and or nitrogen, and N is equal to 1, 2 or 3. Small n is equal to 1, 2 or 3. MAX phage have a layered hexagonal structure with p63 MCC symmetry, where M layers are nearly close packed and X atom fills octahedral site. Therefore, Mn+1 XN layers are interleaved with the A element, which is metallically bonded to the M element. Amaxine are produced by selective etching of A element from the MAX phase structure. Producing Amaxine by etching a MAX phase occurs mainly by using a strong etching solution that contains a fluoride ion, such as hydrofluoric acid, ammonium bifluoride, and a mixture of hydrochloric acid and lithium fluoride. For example, etching of Ti3AlC2 in aqueous HF at room temperature cause the aluminum atom to be selectively removed, and the surface of the carbide layers become terminated by oxygen, OH, and or fluorine atoms. The Amaxine Ti4N3, currently the only nitride Amaxine that has been reported to have been synthesized, is prepared by different procedure than those used for carbide Amaxine. To synthesize Ti4N3, the max phase Ti4AlN3 is mixed with a molten eutectic fluoride salt mixture of lithium fluoride, sodium fluoride, potassium fluoride, and treated at elevated temperature. This procedure etched out aluminum, yielding multi-layered Ti4N3, which can be further be delaminated into single and few layers by immersing the Amaxine in tetrabutyl ammonium hydroxide, followed by sonication. Till date, following Amaxine has been synthesized: Ti2C, V2C, NB2C, MO2C. Another class of 3,2 Amaxine is Ti3C2, Ti3CN, ZR3C2, HF3C2. Another class of 4,3 Amaxines are Ti4N3, NB4C3, Ta4C3. Double transition metal Amaxines are also been seen of the order 212 Amaxine, which is MO2TiC2, CR2TiC2, etc. 223 Amaxines are MO2Ti2C3. So these are all new material of 2D family where the Amaxine group is coming up slowly. This discovery was very recent and lot of researches are going on in this area to find different properties of this Amaxine family. So student, Let us now summarize what we have learned in this module. In two-dimensional material, motion of electron is limited from one dimension and allow freely to move in other two directions. This leads to confinement of electron in one direction. Density of state for two-dimensional material or quantum well is a step function which has been shown clearly during my discussion. Using the expression of density of state of quantum well, occupancy of electron in conduction and valence band has been calculated. Graphene, MOS2, other TMDs like WS2, WSE2, MOSE2, black phosphorus, hexagon boron nitride are the examples of experimentally synthesized 2D materials. Hexagon boron nitride, also known as white graphene, provide 2D insulators. This is the one of the best known dielectric material where the properties of graphene is much better than silicon dioxide substrate. Thank you.